Hello, and welcome to lesson 10.3 on arcs and chords. This is our third out of five lessons on circles. So we're kind of at the midpoint here. We're going to be studying these two terms, arcs and chords, which are kind of just features of circles. If you look down in this picture right here, the chord is the line that goes from one part of the circle to another. So it's basically a line that stretches and touches the circle in two places. So this would be another chord, JH, going from point J to point H. Arcs are just the curved part of the circle that reaches from those two endpoints. So arcs and chords are kind of related to each other. If you have a chord, you will generate an arc. Okay, so let's go through and kind of read this as they present it. A chord is a segment with endpoints on a circle. Okay, so it's a line segment with endpoints that touch the circle. If a chord is not a diameter, then its endpoints divide the circle into a major and minor arc. So let's ignore HJ right now. Let's just focus on FJ. The minor arc would be this small curve up here, and the major arc would be the curve that wrapped around in the other direction from F to G. Okay, so if you're not a diameter, you get a minor and a major arc. Now, if your chord is a diameter, if it goes straight through the center and crosses the circle all the way at its widest point, then you wouldn't get a minor and a major arc. You'd get two arcs that were the same size because you cut it in half in the middle. So they're saying if a chord is not a diameter, then its endpoints will divide the circle into a major and minor arc, like we see in this picture, focusing on how the chord FG divides up this circle. Okay, so reading this again, in the same circle or in congruent circles, two minor arcs are congruent if and only if corresponding chords are congruent. Okay, so they're saying that two minor arcs, like the arc F to G and the arc J to H, are going to be the same size and shape if these chords are the same size and shape. Well, they're definitely the same shape. They're both straight lines. Um, Now, so they're just making that claim. If these two chords are the same size, then they will create the same size minor arc. That makes sense, right? If this chord was a little bit smaller, we'd get a smaller minor arc. If it was a little bit bigger, we'd get a bigger minor arc. So if these two chords are exactly the same size, their minor arcs that they generate, these two curves, should be the same size as well. This is the notation they're using for those arcs. So they're using this little arc above the letters FG. So this is the minor arc FG is congruent to the minor arc HJ if and only if the chord FG, there's no special notation for chords. We're just, saying that's a line segment, but I'm going to read it out as the chord FG is congruent to the chord HJ. If a line segment or array divides an arc into two congruent arcs, then it bisects the arc. Okay, that's directing us kind of, well, let's look at this picture. So it says if a segment or array divides an arc into two congruent arcs, so the arc JG has been divided into two congruent arcs, like JH is congruent to HG. These two pieces are the same size. We've got that congruency notation right there. If that happens, if you're cutting an arc into two pieces, then we are bisecting the arc, right? Bisect means to cut into two even pieces. So this HF is bisecting JG right now. Now this part says if a diameter or radius of a circle is perpendicular to a chord, so right here we see that 90-degree angle, so we can tell that our diameter is perpendicular to this chord right here, then it bisects the chord and its arc. Okay, so if we have a perpendicular line, then if we have a perpendicular chord, then that chord is being cut in half by the radius or the diameter, whichever way you want to say it. So an alternate version to kind of, show an example of that not happening would be like this. If I have a diameter and I have a chord, but that chord does not generate a 90-degree angle right here. Like, right, that's not 90 degrees. That's bigger than 90 degrees. Well, then this section and this section will not be congruent. You will not have bisected that minor arc. You will have simply cut it into two pieces that are not the same size. So if you get a 90-degree angle, whether it's right there, further out, doesn't really matter where we put that chord, but if we put it in a way that is perpendicular to our diameter, then these two portions of this minor arc, these two portions will have been bisected from that minor arc. They will be the same length. They'll be congruent sections. Okay, so that's what this is saying. If a diameter of a circle is perpendicular to a chord, then it bisects the chord, cuts the chord in half, and it cuts the arc in half. I believe this one just kind of says that in the opposite order. So the perpendicular bisector of a chord contains a diameter of the circle. So the perpendicular bisector of a chord. So they're saying this chord right here has been cut in half into two congruent pieces. We know it's being cut in half by a perpendicular line because we have that 90-degree angle. So it says it contains a diameter or a radius. So they're saying when they say contain, they just mean that this line is either going to be your radius or if it's drawn all the way across, it'll be your diameter. This theorem 10.5 is really not saying anything different than this one. It's just saying it in reverse order. So this one said if you cut across in half, you will cut the chord in half and you will cut the arc in half if you have a perpendicular bisector. This one says if you have congruent segments and congruent arc lengths, which they haven't put that mark on them, but if you have those congruent segments on your chord, then you must have been divided in half by a diameter that was perpendicular. Okay, so 10.4 and 10.5 are basically saying the same thing. Okay, final idea here, 10.6 says in the same circle or in congruent circles, chords are congruent if and only if they're equidistant from the center. Okay, so in the same circle or in congruent circles, so this will just be in the same one. Chords are congruent, so FG and JH are congruent if they are the same distance from the center. Okay, so if that kind of makes sense to me. So if, for example, FG was further away from the center, if it was like higher up, if I was to draw a chord, up here a little higher, well, that chord would be shorter than this one because it's further away. If it was closer, it would be even longer, right? If it was closer, we'd have more room to make a longer chord. Now, if the two chords are the same distance away, well, then they've got the same amount of room. It doesn't really matter what angle they're at. Well, it does matter that they're, perpendicular here, but I believe it does. I'll leave that to later to piece together. But anyways, if they're the same distance, the chord should be the same length. That's what this final theorem is saying. So FG is congruent to JH. FG, this chord, is congruent to JH only if LX is the same distance as LY. Okay, distance away from the center. So those are the main ideas that we're going to be working with this lesson. Just a quick run through all of them. So first one was that if you create a chord, it's not in the center, you get a minor arc and you get a major arc. Second one was that if you have a chord that is cut in half by a perpendicular line, then you're going to cut the chord in half and you're going to cut the arc in half. If this one is just saying that in reverse, if you have a chord that's been cut in half, then it's been cut in half most likely by the diameter coming through in a perpendicular way. And finally, the last one that we just said, if we have two chords that are of the same length, they're most likely the same distance from the center. Okay, as long as those chords have the same angle, I believe is also a requirement that they're not describing here. Okay, so in the next video, we'll get started on example 1 using some of those ideas.